Hello everyone, July the 7th. Alright, let's go right into it. Kth smallest element in a sorted matrix. Given a matrix where each of the rows and columns are sorted in ascending order, return the kth smallest element in the matrix. Note that it is the kth smallest element in the sorted order, not the kth distinct element. So, eighth, 1, 2, 3, 4, 5, 6, 7, 8, 13. Can we use NumPy to solve this? Yeah, I think so. We can do each rows and columns are sorted. Rows are sorted, columns are sorted. So, I think NumPy has flatten, right? Yeah, NumPy has. Oh, we just change its shape. Reshape it, and so if we do NumPy, let's say import NumPy as np, we're gonna do numpy.array matrix dot reshape 1 and call it k minus 1. Let's see. Size 9 to shape. Alright, so I think 1 minus 1 to turn it into one row. Index 7 is out of bound. I don't know. The reshape is not working, huh? Oh. Import numpy as np. I'm not sure what happened there. Why is every time we're trying to do this? Alright, so we can say numpy.array reshape. It doesn't work? Oh, it reshape into this. I see. So it has to be 0. That shall work. Yeah. It's going to be 300. Yeah, probably it's fine. Oh, hold on. It's not correct. 1, 2, 1, 3. 1, 2. Expected 1. Oh, hold on. Oh, it has to be sorted. So it has to be sorted overall. In the sorted order. Oh, it's not. Oh, okay. It's. Alright, numpy sort. NumPy sort. I forgot. Sort is array to be sorted. Sort A, sort along the last axis. Sort and flatten the array. I think this is the thing. Alright, this one axis axis 0. We sort here. First axis. 1, we sort this. So I think axis equals none. And it can flatten the array as well. So I think what we can do is maybe we can just say dot sort, right? Dot sort axis equals none. Then we can directly call. We don't have to. This one should be right. Yep, let's try this one. That's correct. I don't think that's going to be fast. I think probably slow. Yeah, NumPy is here. All right, so we solved it with NumPy, but we have to solve it ourselves. So the clue is we have sorted on a row and sorted on a column, right? Then we need to find the kth smaller. Basically, it's just to asking is if I have sorted rows and sorted columns, what is the sorted overall order? Right? That's this question. So here 1, 5, 9, 10, 11, 13, and 12, 13, 15. So it's sorted on a row and it's sorted on a column. But all have situation earlier. I think we see a 1, 2. What's the case that we got wrong? 1, 2. Yeah, 1, 2, 1, 3. Right? 1, 2, 1, 3. So sorted order, which means so the smallest of each row is on the first column, and the smallest of each column is on the first row. So we need to take those out and we'll merge sort them. Take those out and then merge sort them. Right? And then, because everything else is bigger than that, I'm going to take the second row and the second column, then we merge sort them and then merge with the first one. Okay, so it's going to be a recursion. So we're going to say sort flat, sort flatten sort, right? So flatten sort. So we first take the so the matrix, take the first row and first column, we take it out, merge sort them, right? And then we sort the remaining. And the remaining, take it out, merge sort them, remaining until we cannot. So we have to run a few things. I think we need to write a merge sort. So here's that, and we need to merge. Okay, so we need to merge sort. Okay, so we're going to say def merge sort. We're going to give array 1 a list of int, and array 2 is going to be a list of int. Right? So we'll give 2 arrays and then return a list of int. But the 2 arrays might not have the same, so we're going to say res equals a list, and we're going to say zip longest for a1, a2 in. So we're going to have iter import zip longest. Yeah. So say zip longest, return longest order. Longest is exhausted and erase the style. When the short iterable is exhausted, the fill value is substituted in their place. Or we can do fill value. So I think the fill value is just going to be array 1, array 2, right? And fill value going to be math.inf. So we're going to have to go from import math. Right? So for this, if I cannot do that. Oh, we cannot zip it. Shoot. That's fine. That's fine. We can say array1 dot append math dot inf, array2 dot append math dot inf, right? And then we say ij equals 0, 0, right? And while I smaller than len array1, actually -1, because array1 we add 1, or j smaller than len array2 -1. Yeah, let's do this. n1, n2 equals len array1, len array2. Now we get this, and here I and j. So I smaller than n1. Let's do I1, I2. And then, or I2 smaller than n2, right? And say if array1, I1 is smaller than array2, I2, smaller equal, then rest dot append array1, I1, and I1 plus equal 1, else rest dot append array2, I2, right? And I2 plus equal 1. So I put a smaller up, and once 1 is exhausted, right? Once 1 is exhausted, it will point into the largest, so it will keep going until the next one, and then we escape, and then we say turn, rest. So that's merge sort. So now we have a matrix, right? So we're gonna say, how many layers for I in mn equals len matrix len matrix 0, right? And for I in range m, so 0, 1, 2, 3, all the way to the last one, right? And array1 equals matrix 0, matrix I. Array2 equals for j in range, should be I plus 1. No. Matrix I is the entire thing. It's not a matrix I. It's I, that's the first row, for j, right, until the end, should be I to the end, right? I to the end. I to the end. Because of the 0, 0, and 1, 1, 2, 2, right? And array 2 is going to be for I in range I plus 1 to m. Alright? So we have I, but with I plus 1 to m, and it's going to be matrix I. And what is this? This is I. Oh, it's all I's. Right? And then if the second one, then it's 1. And at the end, when I is, what if I is, and then it's just the only one? The matrix 2 is empty array. It's fine. So array 1, array 2, and then we say sorted array. Alright, now we have a sorted array. Oh, we shall go the other way around. Alright, we get this, and then we do this. That's fine. Hold on. The order, so we get the first one, right? Yeah, so we get the first one out. Sorted will be merge sort. We merge sort these two. And then the next one will merge sort these two. So what we shall say is res is this, right? And then we shall say res equals merge sort res, merge sort array 1 and array 2. Right, I'll get a new res, I merge sort them. After that, I'm going to say if k is smaller or equal to len res, return res k minus 1. Otherwise, we'll go to the next round, and then we merge it again, and then we check until one that we find it, and that's it. So the runtime is merge sort is on, so it's on, actually they're all the same, so we only need to do one of them. So it's on, merge is on, right, after merge is on. So yeah, on squared, I think it's on squared. Alright, let's see if this is correct. So I think we have a couple of test cases. So one of test cases is this one. This one's a good test case. And we have a second test case is the edge case, which is also good. And third test case is the one that we got wrong. This one's minus 5, 1, give us minus 5. What's the answer for this one? Answer 13. Right, and the last one, I remember, 1, 2, right? 1, 3. This one shall 2 give us 1, right? So here is matrix K, and this is kth smallest matrix K. M is not defined because we don't have M anymore. Everything is M. Index out of range. How does index out of range? I append n1, n2 is the original, and I'm smaller than original. That is interesting. How does this out of range? Yeah, I is smaller than this. They're both small, and then one of them will reach n1 first. When I reach n1, then I am the largest. So I never move. Somebody else move. Somebody else move until they reach n2. Then we shall escape. Let's see. Where did we get it wrong? Let's print array 1 and array 2. I think is this the first one? Yep. 159 inf and 1012 inf. Yeah. So as we start, both are 0, they smaller, and then okay, let's do this. Print I1 and I2. Just trying to observe where things go wrong. So 0, 0, 1, 0, 2, 0, 3, 0, 3, 0, and 0, 1, 2, 2, 0, 3, 0, 3, 1, 3, 2, and so 3, 2 plus 1, and how do we go to, okay, hold on, 3, 1, 3, 1, and 3, 2. How did you get a 3, 2? You shouldn't be allowed. Yeah, how is that possible? If I is I1. There we go. I think we got that one wrong. Got into I. Okay, now try it again. Alright, they'll pass. It's O n squared. Try it. Pending. Judging. Wrong answer. Alright, let's take a look. Wrong answer. What did we do wrong? Correct answer is 7, and we got 11. 7, 11. Yep. Okay, so let me draw it out first, see if our scheme works. So it's 1, 3, 5, 6, 7, 12, 11, 14, and 14. So my scheme is 1, 3, 5, 6, 11. That's first round. Second round, we're looking for number 5. 1, 2, 3, 4, 5, and I return 11 already. I should not return. I should not return. Yeah, because we have to sort the remainder. But man, if that's the case, so I try to sort it in O n squared. If we don't do it, it's going to be. But why did you sort it that way? I mean, we can just, if we have to sort all of them, we'll just sort row by row. Right? Why do you go this configuration? I don't think it solves anything. But we see it, it cannot make it faster. Yeah, but we're not using the information. Like we use, it's sorted on a row, right? And you just merge sort, merge sort, merge sort, merge to all of them. That's O n squared, right? It's O n squared. And using like, I don't even need to use this scheme. I just row by row. All right, I just row by row, and then I just rest is this. For I, if we do n minus 1, right? And we just say res equals res and merge sort matrix I and matrix I plus 1. And remember, what we can do is we can let's say from 0 to this, and we can just skip like 2 at a time, right? 2 at a time. So we can say 2, and then so another 2. So we can do this 0 to n minus 2. Well, basically, we say from 0 to n minus 2, and we're going to do 2 at a time. What if it's even number? It doesn't really matter if it's even number, right? Even number is fine. So we're going to do 0 and this. All right, 0 on this, and I think we can just do 0 to this, right? And we'll go 2. So it'll be 0, 2, and if it's even number, so it's 0, 1, 2, 3. When you take 0, we'll take 2, and that's it. All right. If it's this, I want to take 0, 1, 2, and take 5. So we just check at the end, right? We check at the end. So we say rest equals merge this. We say if, right? If I is smaller or equal to n minus 2, then we merge this. Else res equals merge sort res and matrix I, right? Then after we merge sort, we return this. Yeah, I mean, in this case, we are not using one of the information, which results in O(n) squared. So this is O(n) squared, right? We go, pending, judging. Yeah, this is O(n) squared. But I'm pretty sure, because I'm not using one of the information. This is a merge sort row by row, right? Merge sort every 2 rows. Merge sort every 2 rows. Just say sort the entire matrix by merge sorting every 2 rows. I think it's O(n) squared. I don't think this is the right way to go. So no, it's not. Look at the time. Look at the time. It's very, very bad. Too bad to have too slow. Right? Too slow to have percentage ranking. Yeah, because we're ignoring. Right? We're ignoring one of the things. Right? We're ignoring one of the things because we are only using it's sorted on a row, but it's also sorted on a column. How do we use that? It's also sorted on a column. Well, if it's sorted on a column and we're looking for the kth smallest element, there got to be some binary search in this. We find the kth smallest element. I mean, we cannot be sure. Okay, we know, right? So for each value, we know the numbers that's larger than it must be to the right, on a row, and below it. But that's not true. It could also be below it to the left, because it's sort. Everything larger than 1 will be everything in here, right? Everything larger than 6. We have to go on the first row to find if 6 is not in the first row. That's how we tell, right? That's how we tell. So what are you proposing? Proposing is you're given a value, right? Given any value. I can find in the sorted order where it is, right? Given any value, I can find in the sorted order where it is. To do that, I'm given a value, so I need to run so we're given any value, right? Then the ones, so we know the ones above me, the one to the northwest, up and left, right? That region, they're all smaller than me. because the one above me is smaller than me, the one to the left of me is smaller than me, that everything in that region is small. So I am at least, I know at least I am, for I is I plus 1 squared, right? I'm at least this much. So that many numbers are, actually it's I plus 1 squared minus 1. I'm at least having these number of values that's in front of me, right? That's at least. But then I need to find, I need to know if there are anything that others that are smaller than me. And I also know, right, the one to the right and the one to the down and everybody in that direction, they're all bigger than me. So I don't have to consider. So all I need to consider is the ones that diagonal, right? I'm talking about a big matrix, not diagonals, like the ones that, so to the top left, I have a matrix. So these values are smaller than me. But all these matrices, all the rows and all the columns, and they have extra values. And those values might be smaller than me as well. So I need to count how many there are, right? Which means given a k, right? Given a k, if so, given a k, that's the so k minus 1, right? K minus 1 is the total numbers that is smaller than me, right? So the search can start from somewhere, right? Yeah, I need to find the values who has, to find a value who has exactly k minus 1 numbers that's smaller than it. Right, so given any number, let's say we go for the largest number, right? Given a number, and then we go for the middle. We go for the middle one. The middle one we can find how many are smaller than it. If the middle one have larger or more numbers smaller than it, then we push back to the middle one, right? So we find the middle one again and look for how many are smaller. And if there are too few, then we go out. But we should also move on the move on the rows on the column as well. Hold on. If I flatten this array, if I flatten it, right, can I have an idea? If I flatten it, it'll be easier for me to visualize the binary search. Right? If I flatten the array, then we have a front, we have an end, and we can have a middle, right? So front, end, and we have a middle. That's 8. So 4, 0, 1, 2, 3, 4. This one is in the middle, right? And we're trying to see So it's gonna be 1, 2, 3, 4, 5. All right, we have the middle. So we know that this one, right? We know this one, and these are performing. So given my present position, I know there are 3 values that's smaller than me, right? And 3 values is smaller than me, and I want to see if there are 4 values smaller than me. It should be exactly 4. Okay. The question is how many are smaller than me? So I have 3 that's smaller than me, and I need to look into the rows, like the top row, the second row, and then for each row we do a binary search, and for each column we also do a binary search. Right? For each column we also do binary search to find where it is, and then but in that case we just do rows and binary search, right? We do rows, binary search, rows, binary search, and we see how many. Once we get the value, right? Once we get the value, let's see, like how many are smaller than me. Then what? What if like there are more? If there are more smaller than me, hold on. This is not a sorted, right? This is not a sorted array. At any position, right? If we have, one more time. Let's say at any position, right? And then we can compute total numbers, right? We can use the binary search method. And at any position, we can use binary search to go from each row and each column to find out how many values are smaller than me in total. And then if I am too big, right? If I'm too big, that means there are a lot more. Then I need to go, let's say, row-wise, right? Just shrink on a row. Yeah, I think we can do one direction first, like say the row direction we shrink, and then once we find, but we won't find, but the I and J, let's say these two will eventually. So yeah, so we're starting at the bottom right, and then our first search is going to be finding out which row it's going to be, which row is going to be. So to find which row is going to be, we just pick the middle row, right? And then once we find a row, and then we need to compute how many is smaller, and it'll be easy. So all we need to know is all the columns, right? Not all the column, it is all the columns. So if I'm here, right, for anyone, I'm here, then I know I'm bigger than everybody in this, right? I'm bigger than anybody in this. And if I'm bigger than anybody in this whole thing, but I'm not sure, I need to look for all these columns. Can I not look at the columns? I just need to look at the rows, right? Hold on. Given here, I'm here, so I know, all I need to know is how many in, so I know these are big, right? These are big than me. These are small than me. These are the unknown, right? So all I need to know is within this, how many are smaller than me? I mean, I can do is simply just go row and column and add them together, right? And if I'm here, then all the rows are smaller than me. So all that we need to do is just column, right? We do all the columns, but I also know I'm bigger than everybody else. So all I need to do is the rows, the bottom rows, right? Just need to run binary search on the bottom rows to see how many is smaller than me. And then I can get an idea. So in this case, we'll say we have 1, 2, 3, 4, 5. Right, we add these 1, 2, 3, 4, 5, and then 6. So we have 6 smaller than me in this case. 12 we have 6 smaller than me. And that's larger, right? So if it's larger, then we move it up 0 and 1. Now the middle becomes 5. For 5, we have 2, and then we run this and find out that's a 0. So for 5, we have like 2. So that's too small. So we're going to add 1. So we record, so we're going to be at 12. Right, level is 12. So that's on the row. And after the row is done, then we do binary search on a column. So to do on a column, we say we then pick the front, pick the end, so pick the middle, right? And again, we do the same thing. We have to go all the rows above me to find how many are smaller, and then yeah, I have to do every one of them. I mean, we can check the end, right? We check the end. We only run it if we only run the binary if the end is larger than me, right? And after we check that, then we check all the columns, right? It's the same thing. We check the bottom, and once we're done, we find out this is, if it's too big, then we keep doing. Maybe. Let's try this. Let's try this idea. Let's try. So some many levels of binary search. All right. So we're gonna use bisect, port, bisect. I like to use bisect right. All right. So what we're gonna do is round 1, right? Round 1 binary search to locate the row. How do we do that? So when you say binary search is left right equals actually this is gonna be top and bottom. It's called top and bottom equals 0 and n equals lamp matrix, right? N minus 1, while t is smaller than b, right? And top is smaller than bottom. Mid n equals like t plus b divided by 2, right? So now we have m, and we know the value, right? Now we need to count the number that's smaller. So how do we count? So we go for, right? We go for count equals, so the start with everything. So that's going to be how many m, right? So 0, 1, 2. So it'll be m plus 1 times n, right? M plus 1 times n minus 1. Right, that's the count. So how many? Actually, we can include itself. So we just find if it's k, right? So count, and then we're gonna say for I in range from m plus 1 all the way to n, right? We can say index equals bisect right, bisect right matrix I, right, matrix I, and what we want to find is matrix M, right, M n minus 1. Right, so this is what we're trying to find in all the matrix. We're trying to find the index, right? And every index we find, it's going to be I think it should be like this, right? Which should with your first look, we say if matrix I 0, right, is smaller or equal to matrix m minus 1. If these two are equal, smaller or equal to, then we run this. This will give us an index, right? An index of where to insert. Hold on. What if I have? Say from bisect import bisect right. What if I like this? Say 1, 1, 1, 2, right? And we call bisect right A1. Does it return 3? 1, 2, 3, yeah. So basically, the index will be the count of number of elements that's smaller or equal to myself, right? Smaller or equal to myself, and that's the one we want. And we already say if it's smaller or equal to, right? If it's smaller or equal to, then count plus equal this elif matrix, and that's not possible. So else we can break. That means the beginning of the next row is already bigger than myself, so there's no need to continue. So just go as long as I need to call the count, right? So now it's the count. Right, now we get a count. Now we're going to say if count, right, is equal to k, right, then we return matrix, yeah, we got lucky, m minus 1. Elif count is smaller than k, right? If count is smaller than k, that means we need to move it down. Move it down means top equals mid, right? We need to move it down. Top equals mid. Else, a count is larger than k, too big. So now we can say bottom equals mid, right? Bottom have to go up. And then we keep going until we find one, get out, so find a row. Now, left and right equals 0 and minus 1 as well. And we say while left smaller than r, right? Same thing, m equals left plus right divided by 2, so 2 rounds. And count equals, this way, count gonna equal, so this one will give us a t or a b, let's just call it t, right? So the count is going to be, we have m. M is the column value, right? The column value, and so it's going to be m plus 1 times t plus 1, right? So that's the row and column. That's a total number that is smaller or equal to myself. All right. Oh, I feel like we have lots of equal values. So this method might not work. Count how many. Hold on, I'm here, right? And what if I have lots of values, it's all the same, right? They're all the same as me. And then in this, we'll say, oh, that's too much. Then we don't go up. Yeah, it's like somewhere around there. Now we already said it's too much. Oh. So it's smaller than me. What if it's equal to me? If it's equal to me, I keep counting. No, if it's equal to me, I should not keep counting, because if in the row that beneath me there is something equal to me, then myself, right, I occur, oh, the not a kth distinct element. So I know if I don't include, then I am going to be the first, right? I am going to be the first. Yeah, I should be the first. I should be the first. So no. No, I don't think it should be a bisect right. I'd like to use bisect left. If I use bisect left, and I only allow if this is smaller, right? If I only allow the front is smaller than me, then I go in, and then I use bisect left instead of bisect right, right? I use bisect left. Then I can void. I can void the trouble that I was thinking about of if I have lots of values that's repeated, right? That's repeated, and this one will guarantee I don't count the repeats. Right? I do not count the repeats. Then I will be the first, right? I will be the first. And if it's too small, I can always go down. That's fine. Yeah. And here, given the current value, I have m and t, right? T plus 1, m plus 1. This gives me the total value that's smaller than me. And then we need to, oh, that's actually not good, because we have to go through all the rows ahead of me and all the columns ahead of me to find out, right? Therefore, so I've got all the rows, all the columns, right? All the rows and all the columns. and we are only going to count. So if a row, right, so I think the count is going to be, no, the count is going to be 0, right? I'll just say for I in range, right, in range, all the rows ahead of me, so all the way to T, but not including me. Oh, then we're double counting. And we are double counting. Yeah, we're counting those. And the columns we're double counting. That's fine, we just minus. That's fine, yeah, that's fine. So if I in range from 0 to T, yeah, to T, because I'm not including T. What is T? T is the index, so I'm not including my current row, it's all the row above, right? And we say if matrix I n minus 1 is smaller or equal to matrix T m, then count plus equal to n, right? And else count plus equal to bisect left matrix I and matrix T and M, right? But in this case, I don't think, right, in this case, I don't think it's bisect left. We want to get in everybody, right? So I think this one is going to be bisect right. So this is going to be bisect right. This file is so complicated. I don't think this is the right solution. So count will be bisect right. We have to include every single one that is above me, right? And after I've done that, so that's all the rows. Then we can do all the column in range M, right? Not including myself, in range M. And the same thing, right? We say if the and, so if matrix n minus 1 J is smaller or equal to matrix Tm, then count plus equal n. Else, if it's larger, then count plus equal to bisect right. I have to make it, right? For V in, no, the matrix, what? Matrix II, J, for II in range N, right? Just, we need to make that into an array, right? And then matrix T and M. So this one, right, we want to include everything that's currently smaller or equal to me, right? So yeah, so we go 2 rounds and we say if count plus 1 minus m plus 1 times t plus 1. If this is equal to k, I'm going to say count plus equal this, right? So we change count change the count, and we say if count is k, then we return matrix tm current one. Right. If count is smaller than k, then if it's smaller than k, which means we need more, so we need to move to the right, which means the left needs to equal to m. Else, if count is too big, then right equals m. Until the next one, until we find one. Actually, I think we will find one, right? Yeah, because it always exists. So actually I can do equal, right? If it's equal. Hold on. I don't want to do equal. I want when they're equal, then they will jump out. Hold up. We do a count, and then we move m. Do another count, and move m. Do a count. So we bias towards up, right? So we do a count, and then no, and to move, or we can move whatever, and do a new count. Is not good. Then we move. I don't know. Would it be happening that, you know, it's the count is not small, right? Then left over here, and then we get a new one, and the count is big, and then we move again, and then we move again. And eventually, we say we want to have 2, right? And then we'll move again to here. Then we come out. So I think if it doesn't return here, we probably still need to return here. Return matrix T, and this is going to be L, doesn't matter. Or, yeah. I'm not sure. This looks very, very, very sketchy. Oh, I think we had a problem. The one side I think has to be constantly moving. If I don't move, oh yeah, we have to move. Which side to move? Top. Let's move top. One side needs to move, and this has move left. Want to pass 1, so the first one doesn't pass. We get 13. It's supposed to be, no, we get 15. It's supposed to be 13. We got 15. Oh yeah. Let's see. Step by step, right? Let's print out TMB, and here let's print out. Actually, let's print out TMB at every step. All right. Print out TMB every step, and here let's print out L and R every step. L and R every step. And we need to separate it. so we know which one is which. All right, so we're going to start with what's the value? 1, 5, 9, 10, 11, 13, 12, 13, 15, right? So we start with 0 and 2, and immediately with 0 and 2, we go for 1, right? M is 1, and we find 13. And 13, we say count is 2 times 3 is 6, so I have 6. Right, so we have 6, and also you run all the column from n plus 1. If this, so it should be 7, right? 13, we should get 7. 13, we should get 7, which is not right. Therefore, I say t top equals m plus 1, and then they come out. So 15, right? Not 15. The t is 2, right? Now when I come out, left and right, 0 to 2, right? And then we start. M is going to be 1, going to this 13. That's actually, I think, the answer. And now we try to count. So what we're trying to do is we count all the rows above it. So t is 2, so I in range, so 0, 1, right? 0, 1, I say if the last one is smaller than that, then count plus 3. And the second one is also smaller than that, so count plus 3. So count as 6. I have 6. I'm done with the first round. Now J, M is 1, so J can only do 0, right? So there's 0. Oh, I see. I shall do m plus 1. I should include myself. No, why do I include myself? Doesn't make any sense. No, it doesn't. It's not including myself. So this one, adding the first column, are the things that we did not. And the only overlapping is these two. So all we need to do is, so we do this, and so that doesn't include, and with this doesn't include. So I think what we need to do is here, count equals, we'll put myself in, and minus. This is the thing. I think it should be minus m times t. Right, so m times t. M times t. All right. Now we pass this. Okay. Let's comment out all these and comment out this. One more. Here. Wait. Here. All right. Now let's try the other test cases. Oh, 0, 1, 2. Number 2 failed. All right. Try it. Get everybody back up. Here and here. All right. So the answer is 1. So my answer is 2. All right. Let's write it out. So it's 1, 2, and a 1, 3. Right. So I say the first round, 0 and 1. So we focus on 0, right? And so it's going to be 2. Oh no, 0 plus 1 times 2. That's 2. So count is 2. And then what we try to do is for this will be 1 to 2. So in 1, make sure it's 1, 0 is smaller, yes. So I count, right? Count plus this will give us 1. So count shall be 2. No, count shall be 3. I think we have count is 3. Right? Count is 3, which is too big. Therefore, we say if it's too big, then B bottom equals M. So bottom goes up to this. So we go out as 0. We go out as 0. I see the problem. See the problem. Because we are saying it happens on the first row, but actually it happens on the second row. But on the first row, there are only 1. Or 2. It's 3. We have 3 values. Maybe I shouldn't include myself. Hold on. So I am too much. Right? I am too much, therefore I say it's going to be on the first. But the first column, there are columns that are smaller than me. How do I reconcile that? Like, I am too much, but the reason I am too much is because there's something else smaller in the other rows, and they pushed me, right? Which means if I'm too small, right? If I'm too small, then I definitely need to go. If I'm too much, right? If I'm too much, I think it depends on which row I will end up in. If I am too much, like too many values is smaller than me. So it can be, like we can count this, how many we have, right? And then we add that, and it's too much. If it's too much, and I go up, if it's too much, if I have too many, right? It's too many that is smaller than me. Then I need to go, so this plus this, right? That's basically what it is. We have this and this, right? And I have too many. And that means it could be here, or it could be here, and we don't know. I can see a scenario, right? It could be up there, or it could be down there. But what we do know is if this one is already bigger, but still it's alright, give up. I don't know. What is the good solution for this? Yeah, my solution is too convoluted. Let's see. It's a medium question. I wasn't able to figure out a smarter way. I can do O(n) squared, but it must be binary search. How do you search it? max heap, binary search. All right, max heap. Easy approach is to iterate all and elements into the max heap. The max heap will keep up to k smallest elements. Oh, I see. We do remove the top, which is the largest one. The top is the kth smallest. I have seen this technique used somewhere else. The kth largest element. Ah. O(n) squared log k. Wait, isn't this going to be slower? This is O(n) squared. This is O(n) squared log k. This is O(m)n, time complexity. M plus n. Yeah, I mean, unless I'm wrong, merge sort is, yeah, because merge sort, we take 2, right? And then we take 2, so it's n divided by 2, and each one is O(n). So n divided by 2 times n, so O(n) squared. This is O(n) squared. This is O(n) squared log k, because we doesn't take advantage to make us already sorted by rows and by columns. So this is don't take advantage of anything. We just read through every value and we'll put it in the heap. And if the heap is larger than k, then we pop the top. Ah, yep. Yep. Yeah, so this solution is slower than this. Maybe it passes as well. Maybe. But the merge sort is O(n) squared. It's O(n) squared log k. Okay, we can skip this one. But that's a good idea, right? The top k, we can use a heap to keep track. Alright, I want to see binary search. In a range, min of matrix and max of matrix, where the number of elements in the matrix is equal to k, that value is our smallest value in the range where the number of elements in the matrix, which is less than or equal to the value, is equal to k. That value is our answer. Smallest value in a range. The range has, I don't understand. Keep reading. We start from the left and right. That's the value, right? That's the value. To find the smallest value in a range equal to k, the number of elements hold on, we have a value and we have a min and max. The number of elements in the matrix, which is less than or equal to this, is equal to k. That value is our answer. The value is not a value in the matrix. The value is just a value from min of matrix and max of matrix. We'll just find a value and we'll look into the matrix to see how many values are smaller, how many values are smaller or equal to myself. And if it's k, then the value is our answer. If it's not k, then I decrease myself. So the problem becomes given any value, to find how many in the matrix are smaller than me. Now we can just iterate through the rows, iterate through the columns, and then find which ones are smaller than me. And we use binary search for some of the values. And I shrink. What if I find one that satisfies, but is slightly larger? Keep reading. This middle number not necessarily an element. For every mid, we count a number of elements less or equal to mid. Let the count. If it's larger, then we keep current and try to find smaller. If it's larger or equal to, then we keep the current answer because it's possible, right? It's possible that a count is the result. We keep count, we keep answering and try to find smaller value by searching on the left side. Otherwise, search on the right side. The answer is the smallest value, which causes the number of elements in the matrix, the k smaller. So we make sure that it is smallest, which means if the count is larger or equal to k, then we keep searching. Right? If it's smaller than k, then we search right. If it's larger or equal to k, we keep pushing. Or if it's smaller or equal to k, as long as it's equal to k, we always search on the left side. Equal to k, I search on the left side. Alright, how to count? It's sorted. It's 2 pointers, one to the rightmost column and one to the lowest row, right? If matrix R, C is smaller, we can include the entire thing, right? And the number of row less than or equal to, let's say, C plus 1, yeah? For the next row, if large, then we decrease column C until this is smaller or equal, because column is sorted in ascending order. So matrix, hold on. If this is the last one, is smaller or equal to x, and the number of elements in row R less or equal to x is C plus 1. Yeah. We go to the next row, and then until we find that RC is larger than X, right? Then we decrease column until RC is smaller or equal to X. Because column is sorted. So if RC is smaller than X, then matrix R plus 1C is also larger than X. So, okay, so we just go all the rows, and once this, we go here, right? And then go 1 time, 2 time, go all the way to the bottom. That's the way to count. But we can use binary search for this, right? (115) is 8. We find smaller than 8. Start is 0. C is here. 0. So 0. C is 2. Find 3. And then it is larger, so we decrease C until here, and decrease C until it's smaller than 8. And the R1 is this, C is this. Yeah, so if this one is already larger than myself, then this one is also larger than, so I don't have to consider. So I just keep And then this part, we don't have to, we can even be faster. We can do so we have to go through every row and the column row. It could be m plus log n, right? Ah. Yeah, I know it's binary search, but okay, we can code it ourselves, this one. Yeah, this is just too convoluted, right? It's way too convoluted. Like 2 rounds of binary search. Doesn't make any sense. All right, so for this one, what we're going to do is we have the basically a left, right? Let's just say left and right going to be equal to matrix 0, 0. That's the smallest. And matrix, yeah, it's binary search on the value itself, right? We're not trying to find the rows and columns, but we find the actual value, the exact value, right? And then binary search, so log this value and so we say while left smaller than right and mid equals left plus right divided by 2. Then we need to count. So count is 0, right? Count how many is smaller equal to myself. So this is how we're going to do. We're going to go for I in range n. So we have to go every row, right? We have to go every row. And for each row, we say if matrix, the last one, right? The last one should be I. The last one is n minus 1. If that is smaller equal to my value, right? If smaller equal to the current mid, then count plus equal to n until not, right? If else I probably need to go C. Yeah, I think I need to go C. So count and J n minus 1, right? So this J is count equals to J plus 1, right? Else, if it's not, then we need to find a new J, which you can say J is equal to bisect right. I'm going to bisect right, matrix I, and mid, right? That will give us minus 1, right? So that will be the new J. And then we go back up, because I should not change. I should not change. So we have to do I as well. I count. So while I is smaller than n, right? And if this I plus equal to 1, j doesn't change. If it's this, j changes, but I doesn't change. So this will allow us to count. And we just say if count, right, is smaller equal to k, right? If count is smaller equal to k, then we need to push. We need to find the smallest mid that allows it. So we're going to push it up. So I'm going to say right equals mid. Let's say right equals mid minus 1. It's actually fine because we want to push. Now let's just say equals mid. Right, equals mid. We go slower. We push up slower. And else, if it's larger, then left equals mid plus 1. So we know it's definitely mid is not going to work because the count is hold on. If count is larger equal to, yeah, count is larger equal to, then we write push up. If count is small, that's too small, then left we're going to plus, right? So we can do this until we're good, right? So when we exit, the value we're going to return is left, right? I have a pass here. Try this. New. We hit a problem. Yeah, because it should be which one's giving us issue? This is fine, right? I smaller than n. If it's smaller than mid, we do that. I go to the next one. If it's bigger, then we do this. J at bisect right. I think we can also do is keep going down, right? So J, right? J, if it's equal, will be here. Otherwise, then the J will be 0, right? So if J is 0, J is not going to be 0. J is going to be J can be 0, but okay. Here's the thing. I need to increment every single one. I want I to increment every single one. So this is good. So here we need to do more check, right? So if J is smaller than 0, which means a current start is larger, then we don't have to check anymore, right? So we're just going to break the entire thing. Otherwise, then count plus equal to J plus 1, right? Which means we can do it here, and we just do larger than mid, and we do something like this. If it's larger than mid, we get a J, right? And J is smaller than 0, we break. Otherwise, we do this, and then back up. All right, let's try it again. Now we pass. So this one is I wasn't able to come up with a decent, with a binary search solution, despite knowing that binary search will work. Now, the following solution is from this post. The main trick is to binary search a value between min matrix and max matrix, right? Not a value inside the matrix. Search any value, right? Search any value between this, not a value specifically inside the matrix. For each value, we count the number of elements in the matrix that are smaller or equal to it. The count uses a few tricks. The count goes like this. If the current column, if matrix I j is smaller or equal to value, then all j plus 1 values in row I are smaller or equal to value, right? Otherwise, we binary search for a new j that satisfies matrix I, j smaller or equal to value, and continue. Right? We shrink the search range to the left. Right, to the left, shrink it to the left when the count is larger or equal to k. Right? This allows us to find the smallest value that satisfies the k requirement. Yeah. The final value is the 1, is the answer. Yeah, if it's larger or equal to k, then we shrink. Larger or equal to k. If it's equal to k, we keep shrinking because we need to find the smallest, which is the kth value. So the runtime is interesting to analyze. So it's going to be log max matrix, right? Log max, let's say log m times log m is the binary search, and within each binary search we have to do n and log n. So it's going to be this, right, where n is the range is max matrix minus mean matrix, and n is the size of the matrix. Let's see how long this one takes. Now I think I did it before. Yeah, it's all today. I'm actually curious to see how that. Let's first run this. 156. That is the thing, huh? 156 milliseconds. Well, we hit a 97%. So I think this one shall be slower. Now we can try. So I think we have to import, right? From heap queue, import heap push and heap pop. I think this one shall be slower than this. All right, this is from the first solution of this post. I think it shall be slower than the merge sort solution. Let's see, it is slower. No, it's not. No, it's not, which means the merge sort is much, much slower. Okay, so technically, the merge itself is on, right? This is on, and I take every 2, So this is ON. Oh, I have another one. That is the problem. I have this, that's ON, and this another ON. That's ON triple. Ah, that's why. ON triple. Okay, this one is good. All right, we got to write it ourselves. Come on. The heap solution. The heap solution is a good solution because it's very intuitive, and I like to employ heap queue. It's very intuitive, and I think it can help other problems as well. Question 3, the heap solution from. I still have it? Nope. Here. Yep. All right, let's try to write ourselves. So that's pretty straightforward. So we have a heap, right? We have a heap, and then we want to maintain the biggest. No, we have to. We'll go through the entire thing, and we keep the smallest. But hold on. If we get everything out and sort it, oh, that's going to be slow. This is mn log k. The other one will be mn log mn. mn log mn. And this is log this and n log n, which is like n log n. That's n squared log k. Depends. One might be faster than the other. This is n log n, right? Depending on the size difference between the two. Yeah, I think this one is, but I'm pretty sure if we just like flatten the entire thing, sort it might still pass. Anyway, so for row in matrix, right? For value in row, we say if len heap is equal to k, right? If len equal to k, then heap q dot heap pop it, right? And then heap q dot heap push heap and minus v, because we want the largest to pop to the top. So keep doing this, and then we return minus heap 0 as the top. Yeah, so this is question 3. Nope. That's not correct. Huh. Alright, we keep push. And then if length is k, and pop, which pop the biggest, right? We pop the biggest. And after we pop, we're pushing the new one. To pop, we're pushing the new one. And at the end, No, I think we should push it first. Yes, I think it's wrong. We should always push it first. If this is larger than k, then we pop it. We always push it first and then pop. There we go. That's the solution. We push it first and then pop. right? Push it first, because then we have the sorting, right? And then we pop. Okay. I have one more that I want to try, and I'm going to write it down. So I think this is just, how can I actually do it? The most naive, I kind of think the most naive might also work. Might not, I don't know. This is the most naive, that we don't rely on anything. Right? Don't rely on anything. So this one is on squared log k. Right? It's on squared log k. Most naive will be for row in matrix, for v in row, right? And then v, and then sorted, and then k minus 1. And this is the most naive. Most naive will be on squared log n, because on squared that is to get this sorted is on squared log n squared. Log n squared is 2 times log n, so it's on squared log n, right? So it's slower than this. It's on squared log n. So log n and log m might not be too much different because it's a log, so it's basically the same, we can say. They're not too different. Oh, actually there is a difference. I think log n is much smaller. Log n is 300, right? And this can go to 10 to the 9. So at most, this one is, say 18, right? This one's 18. 18 n log n. And this will be, that's only like 3 n squared. 3n squared and 18 shall be similar to this one, but definitely faster than this. Let's see. Yeah, let's see. This the most naive might actually not be that slow. Right? It might not be that slow. Look at that. It's not slow at all. It's actually fast. Lightning fast. Why? Because, yeah, there's a good analysis in this. The most naive is, it's actually run at 156 milliseconds. Right? And this runs at 196 milliseconds, right? Because K is actually, so yeah, so these two are not, but it is not slow because n is a small value, right? Solution 2 seems to be a better one, but it has log m, where m can be a much larger value than n. Thus, O log m, n log n might not be, they all have n log n, so just n and log n. But it's, I shouldn't compare it to it because these two have the same runtime, right? Has log m. Yeah. But log m is not too much smaller than n itself. Thus, solution 4 and solution 2 have similar runtime, right? On the other hand, solution 3, which seems pretty good, is slower than solution 4 because log k can be much larger than log n. Interesting. Yeah, this is interesting. 4 solutions, and the ones I came up with is so stupid. I cannot believe it. Okay. I'm thinking about merge sort. I was like, that's the only way to use? No, that's not the only way to use. We could have gone with this, right? This is actually even faster. I think it's faster than our first one. Yeah, it's faster than the NumPy. All right, anyway, that's it. That's it for today. I didn't do very well. I mean, I should have tried the naive way first. Anyway, all right, see you guys tomorrow. Adios.